Okay, example 4 asks us to rotate the region enclosed by y equals x cubed, y equals x squared about the x-axis. So we're going back to the x-axis rotation here. We want to find the volume of the resulting solid. So y equals x cubed and y equals x squared. So I put a 0.25 scale on both x and y. If you're not sure, if you just start by graphing them on your calculator, so y equals x cubed and y equals x squared. And if I just do a zoom 6 to begin with, just to kind of take a look and see where they're at, we're looking to create a region where the two graphs intersect somewhere. And it looks to me like it's right in this area here. I can't really tell specifically, but it's definitely not down there or up there. It's like right in here. So if I just maybe go from -1 up to 2, and from maybe -1 up to 2, let's do that. -1, 2, -1, 2. Again, this is assuming you can't just figure it out already. You don't already know this. All I'm doing is zooming in, getting a closer look, looking for an overlapping region. You can see a little bit of daylight in between those, so it's right in there. And if I just use my brain a little bit, 1 cubed is 1, 1 squared is 1, 0 squared is 0, 0 to the third is 0. So they're equal at 0 and 1. So at that point, if I just go 0 to 1 and 0 to 1, there's y equals x cubed, and there's y equals x squared. So there's our region that we're dealing with, right? So if you aren't sure exactly where it's at, you can kind of pinpoint it. And if all the region is a width of 1 or a height of 1, a 0.25 scale is pretty good. The last one had a height of 4, so a 0.5 scale allowed me to be able to fit it on there. You know, like let's say you're going up 16 spaces, you use a 0.25 scale, all of a sudden you have to have 64 lines. So the whole idea here is I want to have as much detail as possible, so sometimes you have to use a really small scale to get some detail in there. If I had a 1 scale, everything would be right in here. It'd be really hard to draw it. Okay, so using a 0.25 scale is necessary in order to draw it. So again, if you're not sure where these things intersect or how much space is going to be used, use your calculator to pinpoint that to kind of help you establish a scale that you might want to use. So if I'm actually graphing this, so I'm just going to go 0, 0.25, 0.5, 0.75, and 1. y1 is x cubed and y2 is x squared. So y1 is x cubed, we'll do that in blue, and y2 is x squared, we'll do that in red. Alright, so one to my table, I've got 0, 0, I got 0.25, 0.01563, which is just slightly bigger than 0. So I'm going to be just barely over the y-axis, almost touching the y-axis. 0.5, 0.125. 0.25 is there, 0.125 is halfway between 0 and 0.25, so right about there. 0.42188, so 0.25, 0.5, so 0.42 probably about here. And then 1, 1 would be right there. There's y equals x cubed. Looking at y equals x squared, I got 0, 0, same point. I've got 0.25, 0.0625, which is just slightly bigger than 0.015, whatever, so about here. 0.5, 0.25 would be right here. 0.75, 0.5625 would be about maybe here. And then we got 1, 1, so there's our other thing. So there's our little sliver of a region. And just like before, I want to shade in that region, so I'm going to shade in the region. There we go. So there is our region that we're dealing with. Now, we're rotating this around the x-axis. I could have just easily rotated around the y-axis, whatever. It's going to rotate around one of them. This is rotating this direction here, which means that we're going to get a reflection below. So the reflection would be, this is the x cubed reflection. Let's see. I want to get the same basic dots here. So there, there's x cubed. and x squared was here, and here, and here. So there's x squared. Now what I want you to see out of this is that we have an inner radius circle and we have an outer radius circle. There's our cross section. And the region in between the blue and the red circles is going to actually have some capacity. The space inside the blue circle alone is empty, so it's hollow. So if I were to chop this out, so if I just took a slice out of this and looked at it, I would have a red circle with a blue circle inside of it, and the region here is going to have actual capacity. Okay. Inside the blue circle is going to be hollow. So if you took it out, you see a hole there, and there'd be actual material out here. Right? The blue radius is this, and the red radius is this. And looking at the picture, the radius is going from the x-axis up, so it's y, and it's also y. There's two different y's. We have two different functions representing y. So it's very important that you get the correct radius on the correct circle. So, looking at the inner radius, we'll call this y sub 1 to give it a name. Y sub 1 is the blue curve. The blue curve is x cubed, so the inside radius is x cubed. Oops. X sub 3. Try again. X cubed. The outer radius is right here. We'll call that y sub 2. Y sub 2 is the red curve, and the red curve is x squared. So the outside radius is x squared. That right there baffles people sometimes. Because people get in their mind, cubed is bigger than squared, so the larger radius should be cubed, the smaller radius should be squared. Let the picture determine what's bigger, what's smaller. Yes, Renee?
How do you know which one's which?
When I graphed them, the blue curve was made by this one, the red curve was made by that one. So I'm just drawing a picture, a line from the axis up to the curve, whichever curve it is. I refer back to which one it is. And again, that's how you have to do it also. Again, you can't get in your mind cubed is bigger than squared, because if you're in fraction world, 0.5 squared is 0.25. Half of that will be 0.5 cubed. So when you're dealing with fractions, each time you multiply by a fraction, you're taking a fraction of the previous number, you're making it smaller. So cubing is bigger than squaring. If I was in the second quadrant, or I should, if I'm beyond 1 here, if I'm going from 1 to 2 maybe, then all of a sudden the blue curve is going to be above the red curve from that point, and then I'd have the outside radius being x cubed and the inside radius being x squared. So again, let the picture determine what's inside, what's outside. All right, once I look at this, the area of this cross section is just going to be pi times the red radius squared minus pi times the blue radius squared. And that gives me overall an area of pi, both of them have pi, so I'm factoring it out, x to the 4th minus x to the 6th. That represents the area of the blue shaded area, this light blue circle here. So again, common factor of pi, this is x to the 4th minus x to the 6th. And the circles themselves, again, I chopped my cross section right there, but they're starting at x equals 0. There's my starting point. And they're ending right there at x equals 1. Again, you visualize the circle's sitting this way. It's moving horizontally, so it's starting here, it's ending there. So my volume on this one's going to be pi times the integral from 0 to 1 of x to the 4th minus x to the 6th dx. And then it's just a matter of evaluating the integral. So, the integral of x to the 4th is x to the 5th over 5, and x to the 6th is x to the 7th over 7, and we're going from 0 up to 1. And if I put 1 in, I'm going to get 1/5 minus 1/7. If I put 0 in, I'm going to get 0. 0 minus 0, 0. So all I have to do is add or subtract 1/5 and 1/7. That's just 2 over 30, no, that's not right. That's the final answer, but let me do it in pieces. This is just 7 over 35 minus 5 over 35. Have the denominator 35. So the final answer is just going to be 2 pi over 35 cubic units. That's probably as challenging a problem as you're going to get right now, where they're going to have this region that's going to have a piece cut out. So there's going to be a top and a bottom of the region, so there's going to be an inside and outside radius. And again, the way you make that decision, going back to Renee's question, you know which graph is which, so that represents which y is which. So this radius is y, this radius is y, but this is y going to the x cubed curve, this is y going to the x squared curve. That establishes which one's which, and it's up to you to determine that. And again, going to this region here, the original graph region, not the reflected region that you create by rotating.